Ladies and gentlemen, welcome to lecture number 2, Data Transmission Impairments in the course EEE 4682, which is Communication Systems. And the presentation outline will run as follows. I'll give a brief introduction to the whole topic, look at the elements of digital communication systems, look at the signal attenuation, noise categories, all the way up to channel capacity. Then I'll end with the tutorial. Now, as a word of introduction, we'll talk about digital data communication system, we'll look at attenuation, we'll look at noise in both analog and digital communication systems, we'll look at channel capacity, noise figure, noise factor, and so on. And then I'll give a tutorial. The elements of a digital data system can be classified as the transmitting part as well as the receiving part. On the transmitter part, you've got the analog digital converter, the encoder and modulator. And on the receiver part, you've got the demodulator, detector, decoder, as well as digital to analog converter. And discussing about this block diagram in a bit more some details, we know that analog digital converter basically converts analog signals to digital. Then you have the encoder, which is basically the process of putting a sequence of characters. These characters could be letters, numbers, punctuation, and as well as symbols into a specialized format for efficient transmission as well as storage. The decoder will do the opposite of the encoder, basically to remove these sequences and then returning the encoded format back into the original sequence of characters. The modulator is a process whereby you add a carrier to a baseband signal, the message, for the purpose of long distance transmission, and also for the purpose of minimizing noise, as well as reducing the size of the antenna. While at the receiving end, you will have the demodulator, which will basically be circuit that will be responsible for removing that carrier so that you may retain the original baseband signal before it is being transmitted to the end users. Signal attenuation means loss of energy. It's a process where the signal loses energy or becomes weaker. And usually this happens when you're transmitting a signal between the transmitter and the receiver that are separated by a wide distance. Usually to mitigate that setup, we use amplifiers, we use repeaters, which will originate a signal before it is restored to the original format. Attenuation decibel is simply 10 log P2 over P1, where P1 and P2 are basically the input signal and the output signal. And this input signal, if you look at the diagram given here, at point 1, you measure the power, which is P1. At point 2, you measure power, which is P2. And P2 over P1, expressed as a log to the base of 10, multiplied by 10 gives you the attenuation at point 2. And this attenuated signal, as you notice from this diagram, is that it will tend to become weaker as it is being transmitted from point 1 to point 2. So what you do basically is to pass it through the amplifier or the repeater, so that the signal can retain its original strength or energy, as shown at point 3. Now, signal attenuation depends on a number of factors, one of which is distance. The longer the distance between the transmitter and the receiver, the higher will be the attenuation, vice versa. And also the type of media, whether it's wired media or radio media, or it also depends on the frequency. The higher the frequency, the lower will be the attenuation, and vice versa. Now, the received signal strength must be enough to be detected, otherwise If it is not sufficiently higher than noise, then it will be buried into noise and to be received with error. Talking about noise, noise is defined as an unwanted signal that falls within the wanted signal. Usually, this signal is electrical in nature. It will be in form of current, it will be in form of voltages. So these voltages or currents that falls within the wanted signal, which is also equally electrical, is basically what is defined as noise. Noise can be classified as external as well as internal. Noise whose sources are external to the receiver is what we call external noise. A noise created within the receiver, within the equipment, is what is known as internal noise. Let's now discuss briefly about external noise. Like we said, noise created, this is noise created outside the receiver. And there are several examples such as atmospheric noise, extraterrestrial noise, industrial noise. The atmospheric noise is basically noise caused by lightning discharge in thunderstorm and other natural electrical disturbances, which produces an effect which is such that it's random in nature, and this noise becomes more renowned when operated in the VHF frequency band, which is 30 megahertz or above. And then we also have extraterrestrial noise. This is noise coming from the sun as well as the stars. The stars and the sun produces some noise which can interfere with the wanted signal as it moves between the transmitter and the receiver via the air interface. Industrial noise, this is noise from cars, aircrafts, industrial machines. It can range from 1 to 600 megahertz. This noise can also affect the transmitted baseband signal as it moves from the transmitter to the receiver. Internal noise, this is noise generated inside the transmitter or receiver or communication cable. It's a function of so many factors such as resistance, bandwidth, and temperature. But far more disturbing is the thermal noise, and this will be discussed in a short while. But before we get there, let's talk about crosstalk. Crosstalk is unwanted coupling between signal parts. It can occur by electrical coupling between nearby twisted pairs. These twisted pair cables is very common, especially in telephone network, whereby you are able to hear another conversation between the sender and the receiver, and that secondary conversation intruding into the main wanted conversation is basically what we call crosstalk. Another example of internal noise is impulse noise. These are non-continuous noise consisting of irregular pulses or noise spikes of shorter duration, and they are usually of high amplitude. They are generated from a variety of causes, such as external electromagnetic disturbances like lightning, or even faults and flaws in communication systems. Impulse noise is usually just a minor annoyance for analog information, but for digital information or digital signals, impulse noise can be very destructive. It can be very serious because it can actually change bits of streams. Maybe where you have ones, these could be converted into zeros, and where you have zeros, that could actually turn out to be a one. And once that happens, it means you've distorted the entire signal that you're transmitting. That is why we are saying for digital information, impulse noise is very serious. The other type of internal noise is the modulation noise. This is noise due to signals of different frequencies sharing the same transmission medium, and this occurs in such a way that the two signals may add or subtract, and the resultant signal is actually noise. It's not wanted, and it could also interfere with the wanted two signals. Thermal noise is another type. This is noise due to thermal agitation of electrons. It's present in all electronic devices and all transmission medium. This type of noise is a function of temperature, meaning it's affected mainly by temperature, it's affected by bandwidth, it's affected by resistance also, among other factors. Thermal noise can be calculated in terms of thermal noise powers, Pn equals KTB, which is herein shown in equation 1, and B is the bandwidth, T is the temperature in Kelvin, while K is Boltzmann's constant, which is 1.38 times 10 to the power minus 23. Related to thermal noise power is thermal noise voltage, which is given according to equation 2. There's actually a length process to derive that equation using maximum power transfer. Suffice to mention, equation 2 shows that thermal noise voltage is given by the square root of 4kTBR, and the R there denoting resistance, while B is bandwidth, is T is temperature in Kelvin, and the K again is Boltzmann's constant, which is 1.38 times 10 to the power minus 23. Another example of internal noise is short noise. This is noise due to random fluctuations in electron emission from cathodes in vacuum tube, or in semiconductor materials, this is noise due to the variation of charge carriers. It can be calculated using the equation shown here, where In is a short noise and is given by the square root of 2 multiplied by the summation of IDC plus 2IO and multiplied by BQ. And again, Q there stands for electron charge equal to 1.6 times 10 to the power minus 19, while B is the effective noise bandwidth, and IDC is the P-N junction current, while IO is the reverse saturation current. Signal noise ratio is defined as the ratio of signal power to the noise power. It's a measure of how much noise there is in the wanted signal. So if we know the noise power, we know the signal power, their ratio expressed in decibel gives us 10 log PS over PN, which is signal noise ratio. Then the noise figure, which is denoted by the letter F, is the ratio of the signal noise ratio at the input to the signal noise ratio at the output. F is a direct measure of the signal noise ratio degradation caused by the system. Related to the noise figure is the noise factor, which is basically the noise figure expressed in decibel is simply 10 log F. Usually the most important question for communication channel is the maximum channel rate at which it can transfer information, and usually theoretical maximum rate at which information passes error-free over a channel is called the channel capacity C. And the channel capacity of a noise-free channel is C2B log 2 M, where B is bandwidth, M is the voltage levels, or discrete number of discrete signals. Next, we have channel capacity of a noise channel. For a noise channel, data rate can be computed using Shannon formula, which is CB2 log 1 plus signal noise ratio, as shown in equation 5. Where SNR is 10 log PS over PN as shown in equation 6. The fundamental limitation of channel capacity is that there are two factors that determine channel capacity. These two major factors are bandwidth and noise. This is a set of references and tutorials. And this marks the end of our presentation. Thank you for listening. Goodbye.